Welcome to the AI Research Roundup. I'm Alex. So today we're looking at a paper trending on X, published on July 28, 2025, about 5 days ago. This paper introduces Geometric Mean Policy Optimization, or GMPO, a new method that outperforms its predecessor by an average of 4.1% on multiple mathematical benchmarks. The paper is titled Geometric Mean Policy Optimization, and the way it achieves this improved performance is really quite elegant. It tackles training instability in a previous method by making one key change, using a geometric mean for rewards, which is much less sensitive to outliers than the standard arithmetic mean. And it is getting attention. Researchers on X are highlighting how this simple switch to a geometric mean gives more stable training and better exploration. The daily paper's post alone saw strong engagement, with over 280 likes. Also, the authors shared their official implementation on GitHub. It looks like you'll find the PyTorch code for training and evaluation, along with visualization methods and even scripts to help reproduce the results. It seems like a great starting point for anyone wanting to experiment with this method. Alright, so this first figure really gets to the heart of the matter. On the left, you see the core mathematical difference. The previous method, group relative policy optimization, uses an arithmetic mean. The new method, geometric mean policy optimization, uses a geometric mean, and on the right, you see the dramatic effect of that change. The plot shows the important sampling ratio over time. This ratio, it basically measures how much the model's policy is changing during training. The previous method, in red, is all over the place with huge spikes, leading to unstable updates. But the new method, in green, is incredibly stable, staying in a much tighter, more controlled range. Okay, and looking at the math behind that graph, these equations show us why the new method is so stable. These are the gradient equations, which are basically the instructions telling the model how to adjust itself to get better. The top equation for the older method uses a summation, like a simple average. This means one single extreme value can dominate the entire update, causing those unstable spikes. But the bottom equation for the new method uses a product, which is the basis for the geometric mean. This approach is much more robust, giving a balanced view that isn't thrown off by outliers. Building on that idea of stability, these plots really visualize the difference. They track the maximum and minimum importance sampling ratios during training. And again, a wider range here means more aggressive, less stable updates. The red line, representing the older method, shows a much wider and more erratic range over time. In contrast, the green lines for the new geometric mean method are significantly more stable. What's really interesting is that this new method is so robust, it can handle a wider clipping range. Clipping is a way to manually limit these ratios, and a wider range allows for more exploration. This lets the model learn better without becoming unstable. Now moving to the main results. This first table compares performance across 5 different mathematical reasoning benchmarks. The metric here is pass at 1, which just means the model got the correct answer on its first try. And looking at the bottom row, our new geometric mean policy optimization method, using the R1 distill model, achieves an average score of 63.4%. This is a significant 4.1% jump over the previous method. And this isn't just a one-off result. If you look at the other model sizes in the table, you see the same pattern. For the smaller 1.5 billion parameter models, the new geometric mean policy optimization method scores a 43.9% average, again beating the older approach. Then, for the standard 7 billion parameter models, it achieves 52.7%, which is also a solid improvement. This consistent outperformance across different models and benchmarks really drives home the point that the added stability from the geometric mean directly translates into better reasoning capabilities. To really isolate why it's better, the authors then conducted an ablation study, which is where they systematically test different versions of their method to see what makes it tick. This table shows the results of that study. Each numbered row represents a different training objective, essentially a different mathematical formula for learning. Row 1 is the original method, and the final row, number 5, is their complete new method. And the takeaway is clear. The full geometric mean policy optimization method gets the best average score, confirming that all its components work together for superior performance. So, to wrap up, this work shows that a simple but powerful change, swapping from an arithmetic to a geometric mean, can significantly stabilize the reinforcement learning process for LLMs. This stability translates directly into better reasoning performance and allows for greater exploration during training. That's it for